As VR technology advances, we can expect to find more and more instances where visualizations are presented to a user in a VR context. However, VR suffers from a perceptual problem called distance compression, where users tend to underestimate or compress the distances that are shown to them. It is currently unclear how distance compression will affect users' perceptions of visualizations. It is currently unclear how user perception will be affected when doing a task that requires them to read the actual height of a bar in a bar chart, for example. It is also important to consider how tasks that compare relative heights, say between two bars in a bar chart, are also affected. To this end, we ran 3 studies which replicate foundational work in the perception of 2D visualizations. In the first study, we compared how looking at visualizations in a virtual environment, both in VR and on a screen, could be affected by distance compression. We took into account different sizes of charts as well as 3 environments which had differing levels of depth cues that would be available in real life. The first environment had very few depth cues and ignored possible cues like luminance and shadows. The second environment added some things in like texture and realistic lighting. Environment had a park-like scenery which included objects of known size, say like a park bench, which the user could use for reference. In study 2, we explored how we could overcome the problems of perspective, especially when looking at, say, a very tall chart where you are at the bottom. We tested various movement schemes which involve fixed platforms that you could move between, teleporting, and an elevator effect. In study 3, we added pie charts to compare people's abilities to compare relative angles to see if it was affected by distance compression. Similarly, we also included scatter plots to confirm the effects of distance compression in a slightly different context. Our results show that virtual reality and the screen visualizations can both suffer from distance compression when the visualizations are presented in a virtual environment. Participants were slightly more accurate in virtual reality, probably because of the ability to use bodily cues like tilting your head up as a reference point. We also found that while reading actual distance from the chart was consistently affected by distance compression, relative comparisons were much more robust to its effects. Of interest, depth cues did not provide any increase in task performance. However, nearly every participant indicated how helpful it was to have a tree, and they finally felt like they were being accurate at their estimations. Designers may want to consider adding things like relative-sized objects to increase users' perceived accuracy and competence with a task, as well as their comfort. Finally, our results showed that independent of how the user moved around and navigated the visualization, having a perspective which gives the whole chart in its overview, such as a far back and elevated perspective, is incredibly useful. Our paper looks at how the phenomenon of VR-based distance compression can affect the perception of visualizations. The design guidelines in our paper aim to inform future designers in implementations of existing visualizations as well as the creation of new ones.